Hello, I'll be talking about finding consensus bugs in Ethereum via multi-transaction differential fuzzing. This work is jointly done with Taesoo Kim from Georgia Tech and Byung-Gon Chun from Seoul National University. On November 11th, 2020, the Ethereum blockchain hard forked. The Ethereum ecosystem went down. The affected services include infrastructure services such as Infura and exchanges such as Binance, decentralized applications such as MetaMask and Uniswap. Around 30 blocks on the forked chain were abandoned, which handled around $8.6 million worth of ETH. The hard fork is considered as Ethereum's greatest challenge since the 2016 DAO hack and received some media attention. This hard fork was caused by one of the two consensus bugs we found and reported 4 months before the date the hard fork occurred. We found the bugs in the most popular Get client. The Get client developers silently fixed the bugs in new client releases, but not all users upgraded. As a result, when the Ethereum transaction triggered one of the bugs, the problem that I described in the previous slide occurred. Our paper describes how we found the bugs. So first, I'll cover the background of Ethereum. The Ethereum blockchain network consists of decentralized clients that implement the Ethereum virtual machine specification. They reach consensus in the network. We define consensus bugs as implementation bugs in Ethereum clients that lead to incorrect blockchain states. Suppose the Ethereum specification says that after transaction X, the blockchain state on the left turns into the blockchain state on the right. A has 3 ETH. Now, if the client Q is buggy, given the same state and transaction X, it might say incorrectly that account A has 2 ETH, which obviously means that Q has a consensus bug. These bugs are extremely rare. Since Ethereum launched in July 2014, only 13 consensus bugs have been found in the most popular Get and Open Ethereum clients. Only 6 of them would have been exploitable on the live mainnet. Preventing consensus bugs is a top priority for the developers, as they have high impacts. They cause network split, which delays transactions. They enable theft, which means stealing of ETH, the cryptocurrency of Ethereum. Heavy investments are made in auditing, testing, and fuzzing Ethereum clients. I'll now describe how existing differential fuzzers find consensus bugs. These fuzzers have actually found most of the bugs. They work as follows. They generate an input blockchain state and a single transaction. They initialize multiple clients with the blockchain state. They invoke the client with the transaction. They compare the output blockchain states. If the outputs are the same, they go back to step 1 and repeat. If they are not the same, then they claim that a consensus bug is found. Existing differential fuzzers test only a single transaction in each iteration. This is the major limitation of existing fuzzers that prevents them from covering the full search space. So what is the full search space? We define full search space as possible values of client program variables in the memory. There can be multiple different client program states that represent the same blockchain state. For example, A has 0 ETH. So it can be represented with ETH 0 and deleted false, or ETH 41 and deleted true. And the existing fuzzers, because they generate a single blockchain state and a single transaction, and they initialize the clients with this blockchain state, they get to test only a single client program state that corresponds to the pre-transaction blockchain state. and they fail to test these other different client program states. So our key idea to enable the fuzzer to cover the full search space is to test a sequence of multiple transactions, thereby testing various pre-transaction client program states which existing fuzzers miss. So let me illustrate our idea with the specific case studies of the bugs that we found, especially the second bug, the transfer-after-destruct bug that we found. So the root cause of this bug is that get carries over the balance of a deleted account object to the newly created account object under the same address. At least 2 transactions are required to trigger the bug. Transaction 1 destroys account A and sends 2 ETH to A. Transaction 2 sends 1 ETH to A. EVM specification says that because after transaction 1, there's no longer A, so A should have 1 ETH, whereas the buggy get carries over the balance and says that A has 3 ETH, which is 1 plus 2. So let us look at this bug in more detail. Suppose that there are 2 contracts or 2 smart contract accounts which are owned by their own code. And so the code is on the left. On the right, we have the EVM and the guest implementation representation of the smart contract A. So when the first transaction is executed, which calls B with 5 ETH, the code of B is executed, which leads to the self-destruct bytecode instruction in the smart contract A getting executed. So as an effect, the EVM spec says that A is no longer there, and get flags the is deleted flag to true for this account object that is referenced by the address A pointer. Now, when the second line is executed, the code of A no longer exists, so we simply send 2 ETH to A. So in the spec, it says that A has 2 ETH, but regardless, A will be destroyed, and get says that the counter balance ETH goes up to 2. After transaction 1, the EVM and get both say that A has 0 ETH because EVM there is no account, in get the object is marked as deleted. However, the problem occurs when transaction 2 is executed, which calls A with 1 ETH. EVM says that A has 1 ETH. However, a bug in get makes it think that the balance ETH should go up to 3, carrying over the balance of a previous object, and the deleted becomes false. So spec says 1, get says 3. It's an obvious consensus bug. So we found this bug, and the goal here is to design a system that automatically generates and tests a sequence of multiple transactions to find bugs like this automatically. Which brings us to the design of Fluffy, our fuzzer. The challenges are as follows. First challenge, how do we test multiple transactions efficiently? The second challenge would be how do we leverage inter-transaction dependencies? And finally, how do we generate high-quality multi-transaction test cases? Fluffy is our fuzzer, and we solve the challenges by modifying existing clients to enable an efficient execution model. We introduce a test case design that encodes inter-transaction dependencies. We introduce context, bytecode, and parameter mutation strategies that reduce erroneous test cases. So the details are in the paper, but in this talk, I'll cover the overview of Fluffy. So from the corpus of a previously executed test cases, we pick a test case and we mutate the test case to generate a new test case, which has multiple transactions with their dependency information, and we execute the transactions on the client, which gives us the output blockchain states. And we also collect code coverage feedback, and we use that info to, if new code paths are discovered, we save the test case in the corpus for future mutations and executions. And if the states are not the same, then we claim that one of the clients has a consensus bug. I'll now go over the implementation and evaluation parts. So implementation of Fluffy is built on top of LibFuzzer using Rust and Go. We support fuzzing, Geth, and Open Ethereum, which are used by 98% of nodes. Fluffy introduces fuzzing harnesses for optimized execution, including in-process fuzzing and skipping, transaction verification, and jump test checking for optimizations, and also provides a crash debugger for finding the root cause of consensus bug crashes. We evaluate Fluffy on different dimensions, including bug finding capability, code coverage, and throughput. So we use a single machine with 12 cores, 128 gigabytes memory. We test our Fluffy implementation, a modified Fluffy that randomly generates bytecode rather than using the sophisticated bytecode generation strategy of Fluffy, and EVM Lab, a state-of-the-art fuzzer for Ethereum. We test Open Ethereum and Geth. So for bug finding capability, out of the total 15 consensus bugs that have been found since Ethereum launched in 2014, bug 1 and 2 are new bugs we found. 3 through 15 are previously found bugs. We do not experiment with 3 and 5, which Fluffy does not focus on. We do not experiment with 6, which was fixed by using a different library, 14, whose details are undisclosed. Out of 11 bugs, Fluffy finds 10 bugs within just 12 hours, fails to find bug 9, which requires specific inputs that satisfy tight branch conditions to trigger. This bug was originally found with manual auditing. So for code coverage, y-axis shows the number of covered code paths. So the higher is better. X-axis shows the time. After 12 hours, Fluffy achieves 2.7 times and 1.8 times code path coverage compared to EVM Lab and random bytecode, which shows the effectiveness of Fluffy and particularly the bytecode generation of Fluffy. Next is throughput. Y-axis shows the cumulative count of transactions and fuzzing iterations processed. X-axis shows the time, so higher is better in this graph. And Fluffy achieves 510 times transactions and 55 times iterations compared to EVM Lab. So the conclusion is in this slide. Our problem is to find new consensus bugs in Ethereum. Our solution is to propose a new multi-transaction differential fuzzer. The result shows that we found 2 new high-impact consensus bugs that were exploitable on the live Ethereum mainnet. We can find 10 out of 11 consensus bugs within 12 hours. Compared to EVM Lab, we achieved 2.7 times code coverage and 510 times throughput. Our code is open source. Thank you for listening to my talk.